I would like to give a presentation about Open RAN architecture and private network innovation. So maybe on those on very videos before related to NIB and Matter, but maybe I will just explain a little bit more for those NIB and Matter, because that is one of our innovation. So Open RAN is all about the innovations. Okay, and yeah, I think this is my soft biography. I'm working as a technical lead at the KCC Tech. I've been working in this telecom industry for about 15 years. Before I joined the KCC Tech, I joined in Ericsson and Huawei. And I complete my bachelor degree in Indonesia in Institute of Technology Bandung. Okay, before we jump to the main topic, maybe I would like to give a little bit overview. What is the Open RAN? So I took this slide from the TIP Telecom Infra project. So Open RAN is an initiative to build a RAN solution, either it's 2G, 3G until the 5G, that is based on general purpose hardware and software. So I highlight these three words here. So it's an initiative. Who is the initiative? And the idea is to build on the general purpose neutral hardware and software. So the initiative is for sure is from the stakeholder like the mobile network operator, from the vendor, and the standard body as well, to build this Open RAN open to anyone. Because as we know that nowadays the incumbent vendor, it has a very high barrier of entry to a new player vendor to join in. So that's why all these parties like mobile network operators would like to have a better innovation and competition that required, so other vendor can join this Open RAN system network. So this idea will help the MNO flexibility that offered by the Open RAN through the disaggregation of the hardware and software. So the keyword here also the innovation and the flexibility of the disaggregation. And with those innovation and disaggregation and flexibility, this Open RAN also would like to simplify the RAN in terms of development and operation. How we can simplify is through the virtualization. So the word is disaggregation, innovation, and virtualization. So all those kind of word we'll cover on the next slide. So this is the outline for today's presentation. So I would like to highlight the traditional RAN and versus Open RAN architecture evolution, and how is the Open RAN key concept for related to horizontal and vertical openness. And another key concept is the functional split. And the last topic, maybe I just give a simple highlight about our private network KCC Tech innovation for the NIB and Matter. So let's go to a first topic for this session, right? So the evolution from traditional RAN to Open RAN is driven by the desire for greater flexibility, interoperability, the innovation, and cost efficiency in wireless network deployment, as I had been described before in the first slide regarding the Open RAN overview. So this Open RAN has the potential to transform the RAN landscape, because you can enabling new players to enter the market and fostering the innovation. And for sure, ultimately benefiting will be the network operators and the end users like us, or maybe later the enterprise. And before we take a look deeper, I will explain the architecture evolution from traditional RAN to Open RAN. So this slide is I think you guys always see on other another presentation by maybe from Josel, or maybe you can find in YouTube. So explain about the traditional RAN that is like that's running nowadays, and industry call this architecture by distributed RAN. That's why the D word there is represent the distributed. So on the early phase of 2G and 3G that you can see on the side A there, mostly the BBU and the radio unit is collocated into one cabinet. So if you look, let me point it. So if you look on this example of the cabinet, so this is how it looks like. I took this from the one of the Ericsson cabinet. So the BBU, the baseband unit, and the radio unit is collocated in the same cabinet. And from this cabinet that mostly is down below, I mean in the tower, it will connect through the coaxial cable to the antenna. So in the traditional RAN deployments, the coaxial cables have been commonly used to connect the base station to the antenna with the rest of the network infrastructure. But it makes the cost to build become high and not efficient, because the coaxial cable is an analog analog cable, right? So it will, the longer the cable, it will make the loss from the baseband unit, from the BTS to the antenna. So in later on the next phase of the traditional RAN, the big vendor consortium in 2003, like Ericsson, Huawei, Nokia, and etc., they developed a new interface that flexible and efficient between the baseband and radio unit, that they call it is CPRI. So it's a common public radio interface. So this new interface, the main purpose is to transport the high-speed digital baseband unit between the RRU. So we now have a new terminology that instead the radio unit is now it's a remote radio unit, and to the BBU. So this remote radio unit is moved closer to the antenna to reduce the signal loss caused by long cables that we use on the RF cables before, and lower the construction costs, because you don't need to build another coaxial cable again. Instead, you use the optical fiber as the base construction. And with those presence of CPRI, the RAN architecture now moved toward the new architecture called a CRAN, or Centralized RAN, or many industry also call them this Cloud RAN or BTS Hotel. Because on this architecture, the baseband processing that function is separated from the remote radio units that deploy at the cell site. So the BBU mostly deploy on data center or centralized location, often referred to as a baseband unit pool. So the main idea behind this CRAN is to centralize the resource-intensive baseband processing, such as modulation, those coding, those scheduling that normally perform at each base station. And by centralizing this function, the CRAN aims to improve the resource efficiency, reduce costs, and enable more efficient network management and optimization. And you can see from the connection from the BBU pool, the optical distribution network is used to deploy the Fronthaul link, and only available in location with fiber connectivity. So there is an advantage that you can reduce the CapEx and OpEx reduction, but also the disadvantage is you only can deploy this where there is a location for the fiber connectivity. But still, the CRAN doesn't solve the issue for vendor lock-in. CRAN, and next we move to the vRAN, so it's virtualized RAN. So CRAN and this vRAN is a related concept in the evolution of a cellular network architecture, but they have some distinct difference. If before the CRAN is centralizing the baseband processing function into a centralized location, but the vRAN builds upon the concept of a CRAN and introduce further the virtualization and software-defined principle to the RAN architecture. So involving the virtualization of a baseband processing function and the utilization of a COTS, commercial of the self server. So the main characteristics for sure is the virtual baseband processing and the virtual network function that will build into those baseband processing. The next slide is showing the Open RAN architecture, which is the evolution from those traditional RAN, CRAN, and vRAN, to Open RAN that represent a progression towards a more open, flexible, and interoperable RAN architecture. While vRAN before is introduced the virtualization and software-defined principle, this Open RAN takes it further by promoting the openness, standardization, and vendor interoperability. It's also introduced a new terminology. It's like before we already know the Fronthaul is connection from the RRU to the baseband, and now we have separate CU and DU from the BBU to become a mid-haul. So the link between the DU and CU is mid-haul, and DU as a distributed unit that run the RLC, make, and part of the physical layer, and the centralized unit that handles the RRC and PDCP layer, or SDAP in case of 5G, that this centralized unit can connect to multiple DU and CU, can be collocated with DU or far from DU. So in the summary, this is the evolution from traditional RAN to O-RAN that you can see from the left side, the distributed RAN or traditional RAN architecture, where baseband processing and radio functions are distributed and tightly integrated with each base station or cell site. And the BBU and RRU are tightly coupled and sourced from a single vendor. This architecture is also characterized by dedicated hardware units and limited flexibility in resource allocation. And next to the DRAN is a centralized RAN, so represents shift towards centralizing the baseband into a centralized location known as a BBU pool. And the key function for the CRAN is include the centralized processing, resource pooling, and advanced coordination and optimization techniques. But still, this CRAN also rely on dedicated hardware units. And the next to the CRAN is a vRAN that builds open concept of a CRAN, but introduce the virtualization and software-defined principles. It involves the virtualization of a baseband processing and utilization of a standard COTS, commercial of the self servers. And this vRAN aims to decouple software from dedicated hardware, so enabling the greater flexibility and scalability and resource efficiency. And it also leverages the virtualization technologies such as network function virtualization and software-defined networking. And the main goal is the right-hand side is the Open RAN that represents the latest stage in the evolution, focusing on openness, interoperability, the standardization. So it aims to disaggregate the hardware and software components and promote the vendor neutrality and enable multi-vendor deployments. So this Open RAN is emphasis on open interface. So the open interface on the Fronthaul, the mid-haul, and the backhaul, and standardize the protocols to ensure the interoperability between the different RAN elements. So it promotes also a standardized interface defined by organization like the O-RAN Alliance and also a TIP, Telecom Infra Project. So it will later make the ecosystem of vendor and solution and driving the innovation, the competition, and the main goal for sure is the cost efficiency. So if we look on this slide, right, in summary, the evolution from traditional RAN and finally to Open RAN represent a transition towards a centralized control, virtualization, openness, and interoperability in the design and operation of a cellular network that will later ultimately leading to an open and vendor-neutral RAN ecosystem. Like I had been mentioned earlier in the slide before, the Open RAN use a standardized interface defined by organization like the Oran Alliance. So the Oran Alliance has made several working group to standardize this that you can see on the diagram. At the moment, the latest release is release 3. So they built a working group 1 until 11 from use case and overall architecture, the non-real-time RAN intelligent controller, the near real-time RIC, the open Fronthaul work group, open interface work group, the cloudification and orchestration group, a white box hardware, and a stack reference design work group, open cross-haul transport, and OAM and security. So you can try to have a look and see on the web link that I put here on the slide. So that's the evolution from the architecture from traditional RAN to Open RAN. Let's go to the next second topic for today's session is related to the Open RAN key concept of horizontal and vertical openness. On the traditional RAN that we had been discussed before, right, on the architecture of evolution, is the architecture where baseband processing and radio function are distributed and tightly integrated within each base station or each cell site. So the baseband unit and radio unit are typically provided by the same vendor as a close and tightly coupled system using the SPP. So SPP is a single purpose processor that which only optimized for a certain area and a small number of function. And this traditional RAN also characterized by dedicated hardware unit and proprietary interface. So resulting in limited flexibility and interoperability between the vendors. And the next stage is we decompose the RAN. So in the decomposed RAN that normally is used on 5G, the baseband processing function are split between two main components, the centralized unit and distributed unit. So this centralized unit is responsible for high-level network management, coordination, that it acts as a central brain of the RAN, so making intelligent decision based on network condition. And this centralized unit also provide a centralized view of the entire network, so enabling the operators to manage and control multiple DU and RU efficiently. So this CU communicates with the DU over a standardized interface, so it's changing control information and managing the overall operation in the RAN. While distributed unit responsible for handling the baseband processing. So it's a function like radio research management and also connection to the remote radio units. So this DU receive control and configuration instruction from the CU and execute the baseband processing tasks, including the digital signal processing, modulation, and protocol handling. Then we talk about the horizontal openness, or we can say simply word is the open Fronthaul. So after from the traditional RAN, the BBU is decomposed to become a DU and CU. Then in the horizontal way, if you look on the diagram there on the horizontal, we open the interface. Mostly is on the open Fronthaul because this is the the interface that that on the traditional RAN before is usually is closed by each vendor. So how we open is on the 2007 or 2008, the many vendor built a new interface called the ECPRI. So this horizontal openness in the context of RANs revert to use the open interface and standard that enable interoperability, because we open the open Fronthaul, and compatibility between different components from multiple vendors. So it will promote a level playing field and encourage competition, because operator can choose now a best solution from various vendors. They can mix and match which RRU that they can use and which DU or CU that they can use. So this horizontal openness allow for multi-vendor deployment, reduce the vendor lock-in, and for sure will make the innovation foster and collaboration within the industry. The RAN Alliance and other organizations are working to define and promote this open interface and protocol to achieve the horizontal openness. And after the horizontal way we open, now we open a vertical. So we call it this aggregation. So this aggregation is happen on the hardware. So this aggregation refers to the a separation of different functional layers within a network architecture. So it's allowing for independent development and customization and integration of component within each layer. So it's breaking down the network stack into a modular component so that can be deployed, optimized, and replaced independently. So the key concept of this disaggregation is that a DU and the CU there can be implemented as a virtualized software. So that will be running on the commercial off the shelf or COTS. So both the horizontal openness and vertical openness here is a very important aspect of the Open RAN, because it's focused on openness and interoperability. The next step in the context of network architecture is, after we disaggregate and also the open interface on horizontal openness, then we virtualize the component. So this aggregation, as described on the slide before, is involving breaking down the traditional monolithic network architecture into modular component. And the second thing on this concept is virtualization, that will later involve the abstraction of a hardware resource and the creation of a network function, network virtual function that will be run on the shared COTS. So it will enable the flexible allocation and utilization of a resource. So by combining this disaggregation and virtualization, operator can achieve a greater flexibility, a scalability, of course, and efficiency in the network architecture. So they can deploy a virtualized network function on these COTS, and also enable the efficient sharing of hardware resources across multiple network functions. So the leading is to cost savings and improve resource utilization. So this slide explains that how is the evolution from the traditional deployment, virtualized, and containerized deployment. So I took the slide from Kubernetes slide web page. So in the traditional network architecture, it's rely on dedicated and proprietary hardware device that we call it's a PNF, physical network function. So each network function, such as BBU, its own specialized hardware. Maybe you remember before we used a term is SPP, special purpose processor. And these devices were often expensive because it's locked into a vendor and inflexible, tightly coupled with the underlying hardware. And the second phase is to virtualize the deployment or virtual network function. So this virtualization introduced a new paradigm shift by decoupling network function from the underlying hardware and running them as a software on tops of the cards. So with this approach, the network function were abstract from the hardware and deploy as a virtual machine on the standard servers. So we use a VM, so virtual machine here. So this will enable operators to deploy multiple virtual instance of networks on the shared hardware, on the same hardware. So that will be leading to improve resource utilization, scalability, and flexibility. And the next step for the virtualization is containerization. So the containerization took virtualization a step further by introducing the lightweight, because we isolated the runtime environment known as a container. So we contain those software. So container provide a more efficient and portable way to package and deploy application and service, including the network function. Normally, on the containerization, we use technologies like a Docker and Kubernetes that offer advantages such as faster startup times, efficient resource utilization, and easy scalability. So this network function that before we must create the virtual machine on the VNF, we can package into the containerized, into container, so easy to manage, to deploy, and move across a different environment. So the evolution to this containerization also enables the concept of cloud native networking. So there is a cloud native networking here. So where the network function now developed and optimized for cloud environments. So this approach later will leverage the microservice architecture. So because it's a dynamic orchestration and scalability and agile. So overall, the evolution from traditional to containerization is a revolutionized network design. So this is like what I mentioned before in the Open RAN overview. With the virtualization and containerization, we make the deployment of the Open RAN is simplified. If you remember when I show from those tip slide. So enabling more agile and scalable and cost-effective network that meeting demands of modern application and service. Okay, the next topic will be about functional split. Functional split is also a fundamental concept in Open RAN because it serves several important purposes like flexibility and vendor interoperability. So in overall, this functional split in Open RAN provides operators capabilities needed to efficiently manage the network. Maybe to you guys that already read about the functional split from Wireless, from others source in Google or YouTube. But why we need this functional split? I can give you an answer and make it simple. One of the need of the functional split is because of the use case of the 5G. In 5G, we had 3 different use cases, right? The eMBB, the enhanced mobile broadband, the URLLC, the ultra reliable low latency communication, and the MMTC, the machine type communication. So all these 3 cases have their own characteristic and factors, right? That in terms of the specific QoS, right? So the QoS for the eMBB and URLLC and MMTC for sure is different. So you can split later on the CU and DU to the place that is suitable for each the use case. The second thing is also about network density or densification, like this MMTC. You can put all the CU and DU in central, because the things that for the MMTC is you can handle many device IoT or machine-to-machine communication. So the density is bigger. While on the URLLC, you focus more on latency. And the second and then the third is because also the end-to-end transport availability. So in the urban area and the rural area, the end-to-end transport availability maybe is different, right? And the next thing is the use case of the real-time or non-real-time. So to make it a simple understanding of why we need the functional split is because of the use case of the 5G. So here's the diagram that is showing that how is the functional split related to the OSI layer 1, layer 2, and layer 3, and exactly on you can only explain onto two different split: the high layer split, which is the option 2, or the low layer split that is happen on the Fronthaul. The high level split is on this option 2 involves more extensive separation of a baseband between the CU and the DU. So you split here, this part is CU and this one is DU and RU. So on this split, CU is responsible more on the higher layer, including the packet processing, while on the DU focus more on lower layer function, like on the RLC, MAC, and the physical. So this high level split provides more centralized control and management, because you split on the CU side, and it allows efficient resource allocation and centralized optimization, and so make it suitable for scenario where centralized control and coordination are prioritized. The second split is a low layer split, or LLS. So you split on the Fronthaul side. So normally is option 7.x. So you split here on the layer 1 function. That's why we call it a low layer split. So separation of a baseband processing between CU and DU at the lower protocol layer. And this low level split is more on balance between centralized control and distributed processing. So allow a centralized management and coordination, while enabling also distributed data processing closer to the radio unit. So the data processing is closer to the radio unit. So this split is beneficial for reducing the latency and optimizing the resource utilization by offloading time critical processing tasks to the DU. So the choice between this high-level split or low-layer split, it's depend on various factors such as the network deployment scenarios, the traffic patterns, latency requirement, or maybe the operator preference. And different split also can be employed based on a specific network needs, or maybe the hybrid configuration that we can combine of split. So we also can combine maybe split 7.x with a split 2. So this is a RAN functional split that can be explained that normally the gain consensus, the best option to be adopted is that a 3GPP will recommended option 2 or split 2 for a highly centralized application, such as fixed wireless access. So on this split 2, you split the CU and DU and RU. And meanwhile, the Orange Alliance is a support for 7.x. So we split the CU-DU and in the Fronthaul we split low physical and high physical. And also you can combine split. So you combine splits 7.x and split 2. So you have 3 hardware here. So there is a hardware that functional as a CU, functional as a DU, and functional as a RU. Yeah, I think that's my explanation to the Open RAN architecture and those vertical openness and horizontal openness and functional split. And the last topic that I would like to a little bit more explain again after Mr. Ferry introduced before is about our innovation in private 5G network. So in United States, we have several clients that they would like to deploy the private 5G network in their factory. And before that, they would like to testing it first with a demo network. So this is why the network in box is coming. So as like I think this is the same slide like Mr. Ferry explained before. The objective is to deliver fastest 5G proof of concept, so we can bring this to the customer to deploy on their site and testing with their private network. And it really minimum installation and maintenance required. It also can be used for emergency response into the remote location or temporary events. And for the configuration, I think Mr. Fei already explained before. And this is the how is a network in box requirement. So the first is we need a 5G core and 5G BBU. On nowadays, we already joined cooperation with Celona for the 5G core, and also I think now we getting start with Cisco as well for 5G core side. And one of the client also in Europe, there is a university in Europe would like to ask us to build the network inbox using the Fujitsu core for 5G core. And the second is 5G BBU, CUDU. We had small vendor from China, we call it BTI for this BBU. Celeno also have this BBU, and at the moment we still ongoing testing with the Airspan for this BBU and Ericsson. And another component that required for this network inbox that it's a general equipment that we can purchase in general market is a router, is gigabit router, the computer, the NUC, So it's a small computer that we use for operation and maintenance purposes. So when we connect to this network inbox, we have the interface to remote it. And RP here is mentioned is Raspberry Pi. So if we want to testing the throughput through using the iPerf, so we use the Raspberry. And for sure is the power unit, the PSU, and the RRU. So we manufacturing this network inbox in, there's a two option. The first option here is one big box that we put all together. So if you look on the front and the back, it will be, we put here a 5G core BBU and all those router and NUC in one side, and the other side on the back we put the radio unit and the cabling area. Here's the first option box that we use. So it's a very big box, but it's considerably can be moved and transferable to any place. So it's very military grade. And the second option, we also have a small box that's only a 3U. So before is a 10U, so this one is a 3U 19-inch rack. So we can separate the smaller box to so easy to carry on in the flight or in the car. But of course, when reach the site, there is require a assemble for it. And this is a capability and use case that we normally use for network inbox, like a push to talk, always connected PC, and machine vision. Like this machine vision is like we connect to the AI that will recognize if there is a detect a PPE compliance on the factory, or environmental sensing and private 5G network design. And the second innovation that we had built for private network is the Matter. So this is one of the indoor and outdoor draft test tool that we built in innovation. So exactly, I would like to highlight why we had this kind of a Matter, because normally in private 5G network or private network, either 5G or LTE, in the customer side, they will use CPE. So the CPE will be the cradle point or BTI. So it has their own external antenna. Compared to traditional way that we use now, is we're using the smartphone for accessing the network. So like the draft test tools like a TAMS, like what do you call that, the Acufer, mostly they use a smartphone to test the draft test tools. So it will not be apple to apple if we use those smartphone. That's why we built this draft test tool that using those CPE together, the throughput, the RSRP, the RSRQ, SCNR, so we can make a single site verification after we deploy the private network in the customer premises. So this is one of how does it look like, that it will plot the SCNR and the throughput into the floor plan. So this is one of the customer in Chicago that we deploy in parking lot. So after we deploy this private 5G and LTE, we can see how does it the coverage and the network performance. And the Matter also can provide output files in the CSV format and the map format, so that we can use it as a plots.